I hope now you can see. Can you see the screen, the slide?
Yes, Professor.
Okay.
Yeah.
Okay, I'm not going to touch anything. I'm just going to touch the slides now this time. So hopefully we're not going to cause any problems, okay? Now, why do we repeat what you probably have studied many times here? Because the idea here is to give you really one or maybe maximum two lessons. I'm not sure I'm going to let people in if you keep on being late. Excuse me, it's very important to be on time. Otherwise, I'm going to keep on pressing buttons. Okay? For next time, I'm not going to let anyone in after 10:15 because otherwise you're going to disturb the class. Okay, so the idea here is to have a different approach to thermodynamics. What you're always been taught or exposed to is the classical approach, okay? The approach from the 19th century, an approach of which spawned out of steam machines. That's why it was called thermodynamics. Although, as I said, in thermodynamics, there is no dynamics, okay? There is no time, in fact. There is just infinite time. I'm going to give you really an outline, okay, a basic outline, the minimum set of informations on a more modern approach to thermodynamics, okay? Which essentially is the work of Herbert Callan in the 1960s. And this Laszlo Tisza, which is also a founder of the so-called postulational approach, okay? So we're not going to give, so as opposed to clearly these guys here, Carnot, Joule, Clausius, Helmholtz, Lord Kelvin, who actually founded the classical approach to thermodynamics. And really, all these scientists from the 1800s, they were really concerned with the, at the time, the Industrial Revolution and the very, very sort of life-changing invention of the thermodynamic cycle and the thermal machines. Conversion of energy from one form to another, okay? Here we're more concerned essentially on reformulating the concepts of thermodynamics, reaching exactly the same conclusions. This is very important, but not through the laws of thermodynamics, but through a more sort of systematic approach, which is called the postulational approach here, okay? Or, if you will, an axiomatic formulation, okay? Now, okay, so let's talk about a few concepts here and there. As I already told you, first of all, the misnomer of thermodynamics, okay, is the first thing that you should be concerned about. In thermodynamics, there is really no dynamics, okay? So there is no time evolution as we are used to in real life processes, okay? So in some sense, there is no temporal evolution, okay? Temporal evolution can be described only through essentially differential equations involving time derivatives, okay? The rate of change of velocity, okay, equals to times mass is equal to a force, okay? Something like that. We are not concerned in any, okay, place in thermodynamics with time. So you're not going to be seeing any time derivative per se, okay? So it's not an actual evolution in time, okay? What thermodynamics really is, okay, is the study of equilibrium states of macroscopic systems. And we'll define what an equilibrium state is. In fact, when we talk about state, without specifying equilibrium, we give for granted that we're talking about equilibrium states. And really, you can actually move from one equilibrium state to another in thermodynamics, but not in time, okay? You don't evolve from one equilibrium state to another, okay? You can drive a system from one equilibrium time to another, but the time, in fact, is, if you really want to use a concept of time, you should think of this time as being an infinite time, almost a static process, okay? So the evolution in time never appears, okay? So in fact, what Callan did in the 60s, he started from the actually redefining the nomenclature, okay? So a much better definition would be thermodynamics of equilibrium states, or equilibrium thermodynamics, okay? Or even better, thermostatics, okay? Where static, in fact, hints at the fact that there is no evolution in time, okay? So if we really want to drive a system, when we say drive a system, always picture in mind, I don't know, the concept of a piston, okay? I will use it many, many times here. You can keep the piston fixed at any position. This is a thermodynamic system, right? And well, that is, although it's a constrained kind of situation, it is an equilibrium state. And you can set it in any position, clearly the piston, and you can drive the system from one to the other. But really, we're not concerned in the speed at which we're doing this, because again, it is an infinite kind of time, kind of transition. And so the equilibrium processes from one equilibrium to another should be termed quasi-static, okay? Because they occur on an infinite time scale. And this is the kind of new terminology that Callan introduces, okay? So in your mind, what you should be distinguishing or putting apart is these two concepts, okay? On one hand, okay, we are concerned with everyday life kind of phenomena, and really these are what we call real processes, okay? Almost invariably, these real processes are non-equilibrium, okay? Or non-quasi-static, okay? They're different from the ones that we're actually involved in studying in thermodynamics, or in thermostatics, in fact. For example, the fluid dynamic field around a wing, okay, is a non-equilibrium process. Turbulence is a non-equilibrium process. The evolution, okay, time evolution, how fast the reaction takes place, how much time, for example, and what is the output of heat in time of a chemical reaction, that's a non-equilibrium process. They're all involved either gradients in space and or differentials in time, okay, the rate of change of something. So they evolve in finite time. And so in these real processes, time derivatives, when they appear, they actually have the physical meaning that we are used to, which is rate of change, okay? The rate of change of velocity is acceleration, okay? So when you look at differentials, for example here, a differential of the internal energy du, or of entropy ds, they're actual infinitesimal steps towards a new state. And generally, they will always invariably involve an increase in entropy. Again, I haven't defined entropy. I will introduce it, hopefully, in a fun kind of way later on. But of course, we're talking about irreversible processes, okay? In real life, again, when you have, yeah, let's make the example of cubes of ice. If you put them in a glass, okay, you always have kind of the process whereby the cubes of ice will melt and will into some amount of, for example, of water, right? Of liquid water. You can never see the opposite effect of that amount of water reconstituting the cubes of ice. And this is something that will be involved, that will be related to the concept of entropy, of increase of entropy. And clearly in real life, you always have an increase of entropy, okay? And only in very, very particular situations, you can sort of approximate an isentropic kind of situation. Now, in thermodynamics, again, we're interested in equilibrium processes, okay? Which Callan calls quasi-static processes. So there is no physical time here. Those processes drive a particular system. A system you can think of essentially a large group of atoms or molecules, okay? They will drive the system, these processes, from one equilibrium state. Very often, we always use the word state, but it is an equilibrium state, to another equilibrium state. So when you look at these differentials, du and ds, okay, you have to think them not as actual processes, but virtual displacement from one equilibrium state to another equilibrium state, okay, where there is no time. So again, think of the piston. We're not concerned in knowing the speed at which we're moving the piston. We're ever so slowly going from one equilibrium state to another equilibrium state with an infinite time through a quasi-static process, okay? And those systems, or those quasi-static processes can also be reversible or isentropic in some sense, ds equals 0, or irreversible, okay? So that's very important, okay? This distinction is quite important. Now, what is the information that thermostatics provides about real processes? Not very much, in the sense that you're not going to be able to solve a chemical kinetic evolution in time kind of problem with just thermodynamics, nor will you be able to solve the fluid field around a wing, okay, with just thermodynamics, okay? You need some non-equilibrium kind of information. But what thermodynamics really provides, okay, as in terms of information about real processes, okay, is the direction of their temporal evolution. Again, there is no time, but thermodynamics will certainly supply the information that if you have, for example, a mixture of hydrogen and oxygen, the spontaneous direction towards which the system of hydrogen and oxygen will evolve is a direction where they will have reacted exothermically into essentially water vapor. So there is a change in composition and a release of heat from the original sort of chemical energy stored in the bonds. But also think about a mechanical system where you have a concave surface and you leave a ball, okay? Thermodynamics will not tell you how many times this thing will oscillate around an equilibrium point, but it will certainly tell you the direction of the ball will take from the initial state towards the final equilibrium state, which is the lowest part of clearly of the concave surface, okay? So this is very important, okay? Some people call it the arrow of time, okay? thermodynamics will not give you any sort of notion of what the temporal evolution will be, but it will definitely tell you where the arrow of time is pointed, okay? Where the system will spontaneously go to, okay? In search, so to speak, of a spontaneous equilibrium point, okay? Now, this is one of the many sort of characterizations of thermodynamics. You have to, thermodynamics is a very broad kind of word. In some sense, what we're interested here, the thermostatics part, okay, or equilibrium thermodynamics is concerned with quasi-static processes, okay? Again, processes that evolve, so to speak, in infinite time from one equilibrium state to another. And they can be, again, reversible or irreversible. There is also, the non-equilibrium thermodynamics, and I'm adding this here simply because to distinguish it from equilibrium thermodynamics, because it's involved with processes that are actually real, okay? And they evolve in finite time. And simply because they can be fully non-equilibrium problems, but there is a sub kind of branch of non-equilibrium thermodynamics that is essentially concerned with processes that are close enough to the equilibrium, okay? So they still evolve in finite time, but they're quite close. And these are, I won't touch on this anymore, but just to give you the information. These are very important processes because they can give you a lot of information on constitutive relations. For example, those that relate fluxes of mass of extensive variables and generalized forces, like Fick's law, for example. Fick law is a law that relates the mass flux, the molecular mass flux, and the gradient of concentration. So whenever you have, for example, a gradient of concentration, the mass flux will essentially be directed towards the lowest concentration areas from high to low concentration, okay? But again, this is a characterization. Here, we're only going to be involved with equilibrium thermodynamics. Okay, can you hear me okay?
Yes.
Okay, great. Fantastic. For me, it's great to know that because I don't have to re-record anything. Okay. So again, we haven't really said anything until now, but it's very important to put things back into the right definition. Otherwise, we're not going to be able to understand. Now, I'm going to stop here for a second because what Callan does with sort of this new redefinition is not inventing anything new, okay? He's just redefining thermodynamics in a more sort of formal and rigorous way, okay? What he's doing is he's using a so-called postulational, as I said, or axiomatic approach. Now, in order to understand what a postulational approach is, we have to remember the difference that there is between inductive reasoning and deductive reasoning. So I won't be doing a philosophical kind of lecture right now. I'm totally not qualified for that. But you can think of this. You can think classical thermodynamics as being an inductive theory. So it uses inductive reasoning, okay? And the reason for that, I guess, is because it really started from experimental observations, okay? So it started from the analysis of these thermal machines that were, in a lab, in a laboratory. So they were collecting lots of experimental data. And so the natural setting, okay, in a way, of thermodynamics in the 1800s was the setting of sort of an inductive theory. What is inductive reasoning? Well, it's when you begin essentially with data, okay? Some data, which is by itself limited, right? You cannot have fully comprehensive data on everything. You have a set of data. And from that data, you determine essentially some general conclusion, okay? Now, this conclusion is, to the best of your expectations, probable, okay? So I'll give you an example. Suppose we have the set of data about cats, okay? And we have, in this room, okay, for example, we have 3 cats. And my observation is that these 3 cats are black, okay? Black in color. That's my data. I can conclude, okay, that all cats are black, okay? Now, it's a probable conclusion, but it may not be accurate, okay? Inductive reasoning, okay? On the other hand, the postulational approach, which I'm going to be talking about now, is founded more on deductive reasoning, okay? So by deductive reasoning, what I mean is the following. You essentially establish or begin with statements, okay? The postulates, okay? Or if you will, premises. And those you assume to be universally true, okay? Now, given these postulates or these premises, then you determine essentially all conclusions that must be true or certain, not probable, but certain, based on those laws. So for example, so you build your own theory, essentially. So I'll give you an example of this. I can tell you that a postulate may be all men will die. They're all mortal, okay? That's a phrase. It's very, blunt, and I assume it to be true, okay? Then if that is the case, okay, if I take a person like Joe, okay, and I verify that this guy is alive and is a man, then the conclusion is Joe will die. Joe is mortal, okay? Now, as you can see here in this case, we're not talking about data or anything. We're not sort of picking people at random and checking whether they're mortal or not. We started from a very basic rule, okay? Now, the two approaches may be equivalent, okay? But clearly, this other one is more comprehensive to some extent. So what Callan does in reformulating thermodynamics is he makes a series of these postulates. I'm going to give you 3 postulates, which are the basic set. He uses, I think, 4, but it doesn't matter. I mean, these are the 2 or 3 basic concepts, postulates. And what these postulates do, they give you the simplest formal solution, okay, to what Callan addresses as the fundamental problem of thermodynamics. And the fundamental problem of thermodynamics is the determination of the equilibrium state of a system. Again, we haven't defined that yet, okay? But think of this approach as constructing the simplest set of rules that is sufficient to solve this problem of determining the equilibrium state of a system. Okay. Again, have in mind that we want to calculate the final composition of the combustion reaction of methane and air. Okay, this is our goal. Okay. And the reasoning here behind this approach is an observation. Okay, there's always an observation of life. Okay, as it unfolds before our eyes. Okay, so the idea is, the observation is that all systems evolve, or there is a tendency in all systems to evolve towards very sort of particular states, okay, whose properties, we're talking about clearly equilibrium states, depend on intrinsic factors, okay, of the system itself, and not the way in which we reached the equilibrium state, not the history, okay? So for example, again, mechanical system, right? You have a ball and you have like a concave surface. There is a natural tendency of the ball to fall at the bottom of this concave surface. So really, the equilibrium point doesn't depend on how many times the ball oscillates or how it got there. It depends on the shape, clearly, of this concave surface. So it depends on intrinsic properties of the system itself. Chemical equilibrium is the same kind of thing, okay? The equilibrium state will depend on the composition, the initial composition, the temperature, the pressure, on these macroscopic sort of intrinsic properties of the system, okay? And then it will reach spontaneously this equilibrium point. Now, clearly, these equilibrium points or states, they are time independent, completely time independent, and they're called equilibrium. We call them equilibrium states, okay? So that's what it is. So again, the problem here in an axiomatic formulation, in a deductive approach, is to formulate these postulates. So what Callan does, he first starts with defining what a system is, and in fact, he defines a particular system called simple system. Now, first of all, what is a system? Essentially a piece of matter, okay? A mass, which is homogeneous and isotropic. It could be a gas, it could be a solid, okay? So it's a macroscopic, essentially, collection of molecules or atoms, okay? Think of it as always being homogeneous and always being isotropic. So there is no gradients, okay? In intensive variables, there is no gradient of temperature or anything inside this system, okay? Now, the simple system will interact, okay, will exchange something with the surroundings through essentially the exchange of work, which can be exerted, for example, through volume change, okay? And through chemical and thermal interactions as well, okay? So for example, you can have, well, I don't want to say the word wall because I will introduce them later, but really wall is the word. It can be a permeable wall, for example, so allowing mixing, for example, or allowing heat to go through, okay? So it's a system that can communicate with the outside world through the exchange of work, heat, and chemical interactions, okay? So postulate number one sets the stage in a way, mathematically. It will say that there exist particular states, which we call equilibrium states, of these simple systems, okay, that can communicate with the outside, that on a macroscopic level, we'll see what that means, because you can also be concerned with the microscopic level of the actual molecules, okay? But we'll see this later on. These equilibrium states are microscopically characterized by extensive variables, okay? Internal energy, U, volume, V, and if you have multi-species, okay, multiple constituents in terms of molecular constituents, the composition in terms of the number of moles, N1, N2, and K of the K constituents. So essentially what we're saying is we're defining for this simple system the actual phase space, okay, the space where we should be working mathematically, okay? And this space is U, V, and N. N is a vector in this case because it has many components. So internal energy, volume, and number of moles, okay? These are extensive variables, okay? I'm going to go back to a more formal definition. There is actually a mathematical definition of extensive variables and intensive variables. But you should think of those as bulk variables as opposed to intensive variables that are considered field variables, okay? Now, why are they more sort of formally suitable to describe an equilibrium state? Well, essentially because field variables or intensive variables are really variables that in a continuum can vary from point to point, okay? And so they're really more sort of suitable to describe non-equilibrium states, okay? Where you have a field. By field, I mean a function that changes from point to point and in time. And so you also have gradients of those variables, okay? So when you talk about extensive variables such as U, V, and N, okay? So this is a point coordinate of your phase space. If you identify that point, that is an equilibrium point, okay? If we move from one equilibrium point to another, okay, you've done a quasi-static process from one equilibrium point to another, okay? Essentially, this is what the postulate number 1 says. Extensive variables are defined rigorously as additive over constituent subsystems. Simply meaning, if you take twice the system you had before, you put them together, you have twice the internal energy, you have twice the volume, and twice the number of moles, okay? So they're additive over constituent subsystems, okay? Which is something that intensive variables are not. If you have two constituent subsystems at the same temperature, you put them together, you don't have twice the temperature, okay? You have the same temperature. Now, let's move towards postulate number 2. And before we do that, essentially, we have to introduce another concept. And the fact that essentially this postulate was really independent on the kind of equilibrium state that we are in. Now, what do you mean by kind of equilibrium state? Well, think about it. There is a subtle difference between a formally defined equilibrium state. For example, the actual thermodynamic equilibrium of a mixture of hydrogen and oxygen is really a very hot mixture of water vapor, right? H2 plus O2 gives water. Or methane plus oxygen gives CO2 plus H2O. plus heat, okay? That's the natural, so the spontaneous way. But think about the fact that a mixture of hydrogen and oxygen can also be kept quite low temperature. And we can keep it from reacting, right? For example, we can keep it as hydrogen and oxygen. It's, formally speaking, a metastable equilibrium state, okay? But we can force it, we can sort of constrain it, because we are keeping it constrained at low temperature to keep to be just a non-reactive mixture of hydrogen and oxygen. And in itself, it's not going to change, so it's an equilibrium state. But it's a constrained equilibrium state. Okay? And we have infinite ways of choosing this temperature. And so there are infinite metastable equilibrium states. Again, if this is a little bit too tricky to visualize, think of a piston, okay? How many ways can we force the piston to stay in one position? Infinite ways, right? So there are infinite metastable equilibrium states or constrained equilibrium states, okay? However, and this I'm anticipating what I'm going to say later on, you can also release the piston, right? You can release the constraint. And then, well, we know that there is a special direction that the system will take. There's a special sort of evolution that the system will undergo, which is a spontaneous direction, right? Remember the arrow of time? And this is what we have to deal with eventually. Okay, what is that direction? Okay. But for the time being, postulate number one says that any equilibrium state, even metastable state or constrained equilibrium states, are determined by these three variables, u, v, and n. So whenever I move the piston up and down, okay, of this system, I'm actually exerting volume change through an impermeable wall, okay, a rigid wall, and I am changing, okay, the equilibrium state from one to the other through quasi-static processes, okay? Now, what kind of geometric surface does this point, this coordinate describe? We can call it the manifold of constrained equilibrium states. So think of it like a surface, okay? It's some kind of surface, okay, of this phase space u, v, and n, okay? Again, this is a concept that we're going to use later on. Nothing special. I haven't introduced any sort of major or complicated, let's say, concepts here. This is one way you can visualize it. You have a global equilibrium state, which is like the bottom here of this potential well, if you will, but you can also keep with a constraint somehow your system over here in a local minimum, okay? And you can by changing the system, for example, by changing the temperature, you can, again, like a hydrogen and oxygen mixture, you can keep it in a metastable state, okay? And describe essentially this manifold of constrained equilibrium states, okay? I will use it later. Maybe I should have anticipated this figure. This is something that is a manifold of constrained equilibrium state in some sort of phase space. Again, don't look at the entropy here. We'll define it later, but this is a surface, okay? And we can move the system up and down, okay, this manifold, okay, by using constraints, by, again, pushing the piston up and down. So to drive your simple system around this manifold of constrained equilibrium states. Obviously, we haven't addressed the concept of spontaneous equilibrium that we're going to do with postulate number 2, okay? What are constraints, okay? Well, what is this piston? Well, the best visualization of constraint is really walls, right? I already anticipated this before, walls. So again, you have a system which is simple, right? Like this, for example, that can exchange essentially heat and work, okay, and matter, okay, or through these constraints or these walls. So really we can classify these walls, right? And by moving these walls, you can drive the system, the simple system, from one equilibrium state to another, okay? So these walls can be rigid or mobile. Again, simple piston, okay? You move essentially, a mobile wall is what a piston really is, okay? And you can exchange, for example, mechanical work. They can be impermeable or permeable if you let certain species or mass through, okay? So you have chemical interaction. But they can be adiabatic or diathermal, okay? They can let or not let heat through. This is the only way in which you can sort of manipulate the system, through these kind of special walls. Again, the piston is an actual wall, okay? Think of adiabatic and diathermal walls. They're a little bit more complicated to visualize, but again, we can all sort of classify them as walls, okay? So, for example, well, if you put together a rigid, impermeable, and adiabatic wall, you're not exchanging anything with the surroundings. So the system becomes isolated, completely isolated from the surrounding. It cannot do anything. We cannot communicate with the surrounding in any way whatsoever. If it's only impermeable, we call it closed. It cannot exchange matter, but it can exchange heat and work. Okay, so a piston is a closed system, for example. This is the case, for example, if you have mobile walls that are also adiabatic and impermeable, you're not letting any heat or any mass in, but you can move around the walls and change the volume. And so we can go through a quasi-static process from this point here to this point here, right? Your composition will not have changed. So N will remain completely the same, the number of moles, okay? But the volume and the internal energy will have changed, okay? For sure. And clearly this is a situation when you have exchange of only mechanical work, okay? There is no heat. So we can very easily write down the fact that the difference between the two metastable states, the two equilibrium states, U2 and U1, is equal to what? Is equal to the mechanical work done, which is P dV integral between V1 and V2. There's a minus sign clearly because there's positive work done when the volume decreases, so when dV is negative, okay? And this is all stuff that we know, and think about it to some extent. The conservation of energy principle, which was contained in the first law of thermodynamics, is really contained in the first principle or in the first postulate here, okay, directly. We can even consider, for example, walls that are all not only mobile but diathermal, so they can let heat in and out and still impermeable. So we can go from this point to this point here through the exchange of heat and work. So again, N stays the same because you don't have a variation of composition. And now in this case, the variation of internal energy will be the sum of mechanical work and heat. And these two are really indistinguishable, as we know. I won't go into any detail here in terms of imperfect differentials and perfect differentials. You know that already, so I won't stress too much on the classical, let's say, definitions here. So again, postulate 1 indirectly contains the notions of conservation of energy, okay? The fact that you can change the internal energy by either heat, work, or heat, or both, okay? Or any combination of both as indistinguishable energy forms, okay? And these, well, there are a few definitions here. I'm going to give you the slides. I really don't want to waste too much time here. Again, things like entropy I've not even introduced, so I don't want to touch on these definitions. But again, possibly one of the most important ones is the difference between exact differentials that can be expressed essentially in this form, okay, and inexact differentials like work and heat, which cannot have this particular form, okay? But there's some can be expressed as a differential, an exact differentials, okay? But my goal here is to skip all the formal definitions, mathematical definitions. We'll have enough of those later on, don't worry about it. I really want to move towards the second postulate, which is really the core, okay, of the postulational approach. Now, what have we seen so far? We've seen that by manipulating these walls, these constraints, a simple system, which is a non-isolated system, it can communicate with the outside, can move essentially from one equilibrium state to another, okay? So we can move the piston, we can allow heat in and out, and so on and so forth, okay? And in doing so, we've said that the point U, V, and N can describe a certain manifold of constrained equilibrium states. A certain, say, surface on the in the phase space, U, V, and N. Okay. Now, there is an even more fundamental question, because remember that we're really concerned not just with any equilibrium state, but with this spontaneous equilibrium state. An equilibrium state that will be reached spontaneously if we do not constrain the system. So in order to do this, we need to introduce this concept here that you see depicted, which is the concept of an isolated composite system. And what an isolated composite system is essentially an isolated system. So this is bold line. It's essentially a wall that is rigid, okay? It's an adiabatic wall, and it's impermeable. So it doesn't let anything in or out. So this system here as a whole is completely isolated from the surrounding. But it has this particular feature that is a composite system. It's composed of several, in this case, of two subsystems, which are divided by an internal wall, an internal constraint. So in your mind, picture this as a cylinder which is completely isolated from the outside world, and you have an internal piston, okay, with some gas, okay? In fact, the piston could be anything. It could be also a permeable wall. You could have hydrogen and oxygen here, and you can sort of mix them if you remove this impermeable wall. But the really easier picture is that of a piston, right? Now we don't have a piston that you can move from the outside. You have an internal piston. You see, we can still constrain it, okay? But we can also do something very special. We can let it go. We can sort of remove it, okay? Of course, intuitively, it's like a little game, right? If you think about it, so it's like you can sort of build it, in fact. And And if you conceptualize this, we can set the internal piston here, dividing these two subsystems, alpha, in this case, alpha and beta, in an infinite number of ways. You can move it in an infinite number of ways, right? But intuitively, you know that if we let it go, the system will evolve in a special direction that will tend to equilibrate the pressures, right? We all know that. The tricky part is, how do we formally or mathematically describe this, okay, in a theory? It's a very intuitive concept. It's the arrow of time that it's inbuilt in all of us that, lets us know that you cannot recreate 2 cubes of ice from water, but you can melt 2 cubes of ice into water. There is a special direction, right? So how do we formalize this? Again, another example is if these two subsystems are a hot part and a cold part with an adiabatic wall in between the two. If we remove this wall, well, heat is going to flow from one system to the other. Now, we know intuitively that the spontaneous equilibrium point will be a point where the temperature is uniform. So some heat is going to flow from the hot to the cold, not vice versa. So again, the problem is to characterize exactly this, okay? So again, let's go to the piston. Let me read this. The internal constraint can be a piston between 2 subsystems. It can be fixed in several positions, and the equilibrium point for each subsystem, again, will describe U, V, and N, a surface which we have called the manifold of constrained equilibrium points. But, and this is the actual question, what happens if we release the internal constraint? We let the piston free, remove the internal constraint. The fundamental question is, where will the equilibrium state for each of those 2 subsystems spontaneously move to? Okay, that's what we want to answer. And Callan has formalized this in the second postulate, okay? And we have to think about it, if we want to do it rigorously, we have to introduce some quantity, and the easiest way that comes to mind is an extremum principle. So we introduce some quantity and we say, okay, the system will evolve so that this quantity, for example, is maximized. And it's no wonder that this quantity in particular is called entropy. Okay, so this is where entropy is introduced. Okay? So this is where the postulate number 2 is formalized. Let me just read it. So, but of course, why entropy? Well, think about it. Let me just open a parenthesis here. Well, what would you do for a purely mechanical system? Wouldn't you use potential energy and say that the system will evolve towards a minimum of potential energy that is at the bottom of the wall of the potential well? If you have the surface here, a concave surface, you would, right? So here the effort is to completely generalize the concept. Okay, we introduce a function entropy and essentially want to maximize that so that we can take care not just of mechanical systems, but also thermal systems, and in general, chemically reactive systems and thermodynamic systems, okay, that can either get hot or cold, they can be compressed, so exerted work on, and they can react. Okay, we want to generalize this completely. So postulate number 2 says that there exists a function entropy S, okay, which is a function of the extensive parameters U, V, and N, okay, of any composite system, which is defined for all equilibrium states and has the following properties, okay? The values assumed by u, v, and n, that is by the extensive parameters, when we remove the internal piston, we remove the internal constraint, and so the values assumed spontaneously, let's say, at the spontaneous equilibrium point, are those particular values that maximize the entropy over all the possible constrained equilibrium states, because we have said that you could have infinite constrained or metastable state, but there's only one that is the spontaneous equilibrium point, okay? That is achieved by releasing the piston inside, okay? And so that particular state now, I'm saying it has the property that it will maximize the entropy, this particular function, entropy, okay? We haven't explained what it is. Obviously, at the point where Callan introduces entropy, he already knows what it is, clearly. And we have given it both a classical definition in the 1800s and a statistical mechanical equilibrium definition through Boltzmann, which is a more of a statistical, clearly, or probabilistic definition. So we know what it is, okay? I'm just postulating here formally that it should be maximized. And of course, if we have time, I'm going to introduce these concepts in a sort of fun way with sheep. You'll see in a second. So now that we've stated this rule, the problem of determining the equilibrium state once the internal constraint is removed, so the spontaneous equilibrium state in a way, is completely solved if you know this equation. If you can write down the fundamental, this is what Callan calls it, the fundamental equation for your system, which is essentially the function of entropy expressed as in terms of u, v, and n. If you can actually express this formal definition into an actual function, a mathematical function, then the problem is completely solved, because all you need to know is find the maximum point of this function, okay? You see how elegant this thing is in some sense, although a little cryptical, because of course you need to give me what entropy is, but we'll see. In a second, you'll see that we can actually recover it quite easily, given a particular system. Okay? By system, I mean, for example, a specific system, a chemical system. It could be your piston with the internal constraint, for example. Okay. Let me stress this again. I'm not interested in this formal definition. I'm interested in the actual equation. Okay. That defines S in terms of U, V, and N. An equation that will allow me specifically and practically to find a maximum equilibrium, a maximum point. Okay. Let's see if I can get to that final picture. There is also a technical postulate, number 3, that I'm going to go over briefly, that sets the basic property of entropy. Okay, we haven't said what entropy is, but at this stage in postulate 3, we're giving it more specific properties. Entropy of a composite system, again, always remember that we're dealing with these special composite systems that are completely isolated, okay? There is just an internal constraint that we can move around, and then we can also remove or release the piston. Okay, so the entropy of these composite systems is, first of all, extensive. It's an extensive quantity, so it's additive over constituent subsystems. So alpha and beta, Okay, I take the entropy of alpha, the entropy of beta, the overall entropy is the sum. Okay, and it also is a continuous and differentiable and monotonically increasing function of the internal energy. So the more internal energy I have, the more entropy I have. Okay, and this is already saying a lot about what entropy actually is. Okay, although it's not saying anything in terms of statistics, okay, it has a lot to do with internal configurations of atoms and energy, okay, that each atom can have. Okay, so in terms of a molecular sort of system composed of a great number of molecules. So mathematically, when we say that it's a continuous differentiable and it is a monotonically increasing function of the internal energy, what we're implying is that the function, the fundamental equation S of u, v, and n can be inverted. Tell me if you can still hear me, because
Yes.
yes, fine, good. It can be inverted. So this fundamental equation, we can recast it in this different form. U of S, V, and N. It's exactly equivalent as before, but now instead of having an entropy-based fundamental equation, we have an energy or the internal energy-based fundamental equation, okay, in terms of the internal energy, okay? So we can reformulate. This is, of course, a summary that I'm giving you, okay? It's a little bit more formal, but again, I'm giving you the juice of the concept. Because we have inverted now, what used to be a maximization of entropy can be completely translated equivalently as a minimum or minimization of the internal energy, okay? So postulate number 2 can be equivalently expressed in terms of a minimum internal energy principle, okay? So when we release the internal constraint, the system will evolve towards a point characterized by S, V, and N, which minimize U, this function U, okay? Now, which is, again, familiar when you look at mechanical systems and minimum potential energy, okay? Let me just say, this is the formal definition of what an extensive quantity is, okay? So we said that the entropy is extensive. So if you take a constant lambda, okay, and you express the function of entropy by multiplying each variable by lambda, the property, the mathematical property is that you can take lambda out to the power of 1, okay, of S of u, v, and n. What does that mean? Essentially mean if you take lambda times the system that you already have, okay, the entropy is multiplied by lambda, essentially. So it's additive over constituent subsystems. You can also say that it's a homogeneous first order function in the sense that you can take this constant out and it's first order because you can have it to the power of just 1. If you have it to the power of 0, then it's an intensive quantity. You see? Because it's not additive over constituent subsystems. If you take lambda times the system you already have, you have lambda to the 0, so 1 times so you have the same amount, the same value as before. And formally, this can be treated with Euler theorem, which we're going to state later on. So it's becoming more and more mathematical as we go along. Again, therefore, I just said you can express, therefore, this fundamental equation S, okay, in terms of u, v, and n, okay? Well, I've written down the components here, but it doesn't really matter. be able to express it, to draw it, you need a three-dimensional space. So just imagine you take one of the species here, you have a growing direction of internal energy here, and you see that through the third principle, entropy increases as internal energy increases in this direction, okay? So it has this particular shape. Okay, and this is your manifold, this is your fundamental equation in some sense, and it's also the manifold of constrained equilibrium. Why? Because, again, picture the internal piston. You move it around, again, and you essentially describe every single metastable point, okay, which is still an equilibrium point, and going from one to the other will be a quasi-static process, and you can move from one equilibrium state by just moving around the piston inside. Okay, and you will describe fully this manifold of constrained equilibrium states. So what you see here portrayed is a quasi-static process between this state here and this state here. In this particular case, you see that you have an increase of entropy. If entropy is this axis here, you have an increase of entropy. You could even move along an isoentropic plane here, okay? But now let's see, and I'll stop there. I guess I have another few minutes. How to visualize the second postulate, okay? So we all accept this visualization here, okay? Postulate number one says that we are in this particular phase space, U, V, and N, okay? Clearly, for simplicity, I haven't shown you the volume here. It's a multidimensional system. And then postulate number two essentially says that an isolated composite system spontaneously evolves towards the maximum of internal energy, okay? Sorry, of entropy, or a minimum internal energy. So now we can express this in the following way. Let's look at these two possibilities. Let's look at an isolated composite system, okay? So we have an isolated system that is composed of two, for example, subsystems, okay? Because it's isolated, remember this, the internal energy of the whole subsystem, which is the sum of the two constituents, okay, alpha and beta, is clearly zero because you cannot exchange any work or any heat, okay, to the outside. So we're actually on this particular manifold of constrained equilibrium, where are we moving? Well, we're moving on this plane here. Okay? Why? Because essentially the internal energy is constant. Okay? The internal energy stays constant. So you see that on this particular plane, the internal energy stays constant, du equals 0. Now, that means that in this particular state, at constant equilibrium, we can move only on this line here, okay? This particular line here. Now, what does postulate number two tell us? It tells us that if we remove the internal constraint, you will maximize the entropy. And so where's the equilibrium point? Over here. This is the unique equilibrium point. In some sense, we have characterized, you know, a very, very important phenomenon that happens in nature all the time, okay? It's actually formally characterizing the natural evolution, spontaneous evolution of systems that we have characterized quite rigorously, which is spontaneous. That is, it's the natural evolution once we leave any source of constraint. We don't keep it metastable somewhere else, but we let it go wherever it decides to go. And there is a special direction, again. Let me just say that we can also have a number two situation for another kind of system, which is an isentropic system. It's not as obvious to visualize isentropic systems, but for the time being, let's think of those as being systems for which the entropy stays constant, okay? Because we said that you can invert the fundamental equation, the equilibrium state, when you remove the internal constraint, will be a minimum point of internal energy. So the S equals S0 is your plane here that keeps the entropy constant. So now the intersection is this line here, and you have to look for a minimum of potential energy. Potential energy grows from this direction into this direction. So the minimum of potential energy, I hope you see it, is still this point A. Okay, but you can move it up and down. You can move it around. Okay, this plane. So again, we have now two formal definitions of equilibrium criterion for both isolated systems. Point A will be a maximum of entropy, where we keep the internal energy constant because clearly the system is isolated. And or if we have an isentropic system, the concept is minimum of internal energy over the plane S equals constant. Okay. Now, we could stop looking at slides now. Yes, and we'll continue next time. I have given you three postulates, and it may seem a little vague, but in fact, it really isn't, because it has nothing more or less than the principles of thermodynamics. And in fact, if I may say so, if you've noticed, the second principle of thermodynamics in the classical thermodynamics is always stated in a different way. You've always seen like 5, 6, 7 different versions of it. You will only see one single version of this particular postulate number 2, okay? So formally, it is, in my opinion, a more rigorous approach, okay? That at least an engineer should have once in their career, okay? It should be exposed to at least once in their career. Let's talk a little bit more about entropy, because we really haven't discussed its significance or its meaning. What is it? What does it measure? Right? This is a legitimate question, right? Well, historically speaking, we have to go back to essentially Clausius, okay? The work of Clausius in at least 1850, where we first see the occurrence of the word entropy. Nothing mysterious. What Clausius really was concerned in, he was really concerned in his inductive approach of thermal machines, okay? Especially of machines that were working with the Carnot cycle, okay? And it was really a quantity that was useful in characterizing Carnot cycles, okay? And he defines it essentially as the heat exchange divided by the temperature. And it was something that for ideal Carnot cycles, when you close the cycle, you would go back to the initial entropy state, okay? It's an extensive variable, okay? Because clearly it has to do with heat, okay? The fact that entropy is directly related to heat is very important, okay? To the content of essentially, ultimately, of energy being added to the system, okay, in terms of heat. It is a function of state, okay? So all these concepts were already there, but it essentially was used to characterize the experimental evidence that one would see by looking at or characterizing the Carnot cycle, okay? Later on, there was a much more sort of intuitive definition introduced by Boltzmann. So when statistical mechanics was first developed, thermodynamic systems were now considered as microscopic systems which were composed of ensembles of a large number of particles, large number of atoms, each moving around with its own energy, okay? So you could actually view the thermodynamic system as both either macroscopically, whatever you can measure macroscopically in a laboratory without looking at the internal structure or the internal particles, but you could also consider it microscopically as motions of individual particles, okay? And Boltzmann essentially introduced an equivalent definition, okay? And the fact that dq over t was completely equivalent to the statistical mechanics definition could be completely proven, okay, mathematically. And what he figured out is that actual entropy, as given, you know, by Clausius a few years before, what it really is, and what really entropy means, is a measure of the number of ways in which microstates, okay? By microstate, I mean configurations of molecules, okay? In terms of position and energy, for example, can be arranged for one given macrostate. So if you have a macrostate characterized by temperature, by pressure, okay, of a piece of matter, if you really look closely, this macrostate can be characterized by, generally speaking, a large number of microstates. How many configurations are there that give us the same temperature, for example? And if you measure those, you take the logarithm. I won't go into details about that, but still, it's proportional to the number of microstates. You get the entropy. The proportionality constant is, in fact, the Boltzmann constant, okay? So think of entropy as the Boltzmann constant plus the logarithm of the number of different microstate configurations. The higher the number of microstates, the higher the entropy, okay? Now, well, we don't have too much time, but I really urge you to look at, now I'm going to switch. Can you still hear me? I hope you can hear me.
Yes.
Okay. Can you see this internet site?
Yes.
Can you see it well, or is it fuzzy? Okay, I hope you can see it well. Okay, I'm going to give it to you. I'm not sure you can read it here, but anyway, can you read it? I'm going to post it in.
Yes,
I always
yes.
suggest this internet site. I think it's a brilliant internet site. It's trying, what this internet site is trying to do is trying to explain exactly this concept, the statistical concept behind entropy, and how entropy is really related to equilibrium states. And there is nothing mystical, there is absolutely nothing mysterious about it. It fully explains why systems have a natural tendency towards moving towards equilibrium state, natural equilibrium states that are characterized by the maximum possible entropy, okay? So it formalizes the second postulate that I just give you on a statistical level. And it uses, well, these things here, which are sheep and fields of grass. Okay? Now, why does it do this? Let's see if I have time. Well, if I don't have time, I'll continue next time, okay? Imagine a thermodynamic system, okay? A piece of, an ensemble of essentially atoms, okay? Now, your atoms can be, for example, visualized as glasses, like this, containers, and the energy that the system has on a microscopic scale can be visualized as packets of energy. You can also have them visualized as quanta of energy, okay, quantum of energy. So these quanta can be exchanged, okay, from one glass to the other, from one atom to the other. Maybe an even easier way is this. Think of your piece of your system, your thermodynamic system, as a big field of grass, green grass. Each atom is a little patch, a little subsystem, a little patch of grass. And these energy packets are essentially sheep, okay, that can move freely around the whole system, the whole grass, okay? So, for example, here we have 3 atoms and 4 packets of energy, 4 sheep, okay? You see already here that there is a concept of configurations. For a given energy level, 4 sheep, you have a number of ways in which you can shuffle around those packets of energy, those sheep that move around. They move around, sheep, right? And they can, for example, all concentrate on one atom. That's pretty improbable. The most probable thing is probably that they're spread around, right? But still, they introduce a concept of configuration, number of different configurations. In fact, here there's a little game. Suppose you have just one packet of energy, just one sheep, and you increase the number of atoms, okay? So you see I'm introducing patches of different patches of your overall field. How many number of ways can you arrange one sheep, okay, one packet of energy in 4 plots of land? Well, obviously 4, either here, 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 or here, right? If I go ahead, 10, okay, number of 10 atoms, 10 plots, okay? I have 10 ways in which I can arrange this one lonely sheep. But now what happens, look what happens statistically, not statistically, by counting the number of configurations, if I increase the actual number of sheep, the actual energy that I'm giving the system in terms of packets of energy. So if I double it, it's already 55. 3, 4, 5. I hope you saw this. 5, 6, 7, 8, 9, 10. 92,000 ways in which I can distribute 10 packets of energy among 10 different plots of land. I can have, for example, 9 packets here and 1 over here. I can have 2, 2, 2, 2, and so on. Okay, these are the total number of permutations that you have available. Okay, this is a number that grows incredibly fast. Okay, as we increase the number of atoms. Look at this: 2 million, 15, and 15, 78 million. Let's see 20 and 20. 2 billion, 69 billion ways, okay? So microstates, because the number of atoms and the number of packets of energy is really huge, we're dealing with Avogadro numbers, okay, 10 to the 23, 24 molecules, and a huge number of quanta of energy being added to the system, we're talking about a huge number of configurations. That's the first thing that's very important to understand, okay? This is an enormous number of configurations, okay? So you can play around with this internet site. Of course, read whatever is inside here, okay? Now, what we have here, and it's no coincidence that we do have it. We have a composite system, exactly what I told you about in Callan's approach. Suppose that you have essentially a system composed of two subsystems with an internal constraint. The internal constraint can be a fence that keeps the sheep from moving from one to the other, okay? So it keeps, for example, all the sheep in the upper part of your field, okay? What happens if I remove now the fence? These sheep will try and move around, right? Well, that's exactly what happens. Okay? You have 6 sheep, and what this is doing randomly, because there is no configuration that is more probable than the other. Wait a minute. Every configuration like this is exactly has the same dignity and the same probability than the others, okay? What if we count them? We count the number of sheep, for example, on the top system. Look at this. All sheep on the top system is not a very probable configuration. On the other hand, 3 sheep on top and 3 sheep on the bottom is what usually happens. If I make it faster, or blazing fast, you'll see that there is a pattern emerging here, okay? Now, I have to stop here, but the spread out solution where you have, originally you had 6 packets here and 0 here, okay? Now I open the fence. Now it seems that the spread out situation where you have 3 on the top and 3 on the bottom is really the most probable configuration, okay? And remember what Boltzmann said in terms of defining entropy as exactly this, as the number of configurations. Well, then the highest entropy is the most probable one. I will go back on this site very briefly if you want to play around with this. It's a really instructive way of looking at entropy, okay? I hope that was clear. Okay, I will stop now presenting and recording. And obviously, if you have any questions, please go ahead.